They should be inside course content. What we do between semesters is we turn a bunch of stuff off. So see that little X right there, you know what that means? It means it's so if you refresh your screen, so they should be inside course content, so you couldn't have got to it anyway. And then we're in number systems, right? And then here's all your handouts. So that powers chart is going to be in there if you lose that. Lecture slides, worksheets, and of course chapter quiz. So as soon as we get through with this tonight, then when is the chapter quiz is due? The chapter quiz is due within 7 days. Okay, y'all understand that? So we're going to finish up this, yeah. So it should be due by then. You know, you can do it. You can.
So it's the chapter quiz is up already for the.
Yeah. So here it is. Should be up. Because so here's chapter 1 topic quiz, which is the chapter we're in. That's the only problem with using that. Using that online book is that the chapters might not be laid out the same, but the content is still there. So you can see what we're going to be lecturing on here. So I give you the titles. So we're going to go into switches, basic logic, Boolean algebra, exclusive OR, exclusive NORs. Somewhere down the line, though, when we get about into here, we'll probably jump to chapter 9 because this is where you get all the data sheets and all the other stuff that would help you replace a part, and there's a bunch of information in data sheets that and what's nice about it now, these data sheets, I think I was telling the class, you know, you used to get these big old books. Now you just go in, type in the part number, and it'll hopefully find some. But keep going too, because a lot of times you get into those places that want to sell them to you, but odds are you're gonna find them. You're gonna find them free. So let me bring up a blank PowerPoint presentation so I have something I can write on. So we can work some of these. So anyone we want to do?
Do from BCD to decimal.
This one right here, this BCD.
Yeah, fifth one, yeah,
no, this one is fine. So this is a BCD number, and we're trying to go all the way around. So first thing I'm going to do is convert this over to decimal. And this is a pretty, and I don't know what happens sometimes. So one way people can do it one way, but they can't turn around and do it the other way. So this would be a 1395 base 10. So this is a code that directly represents the decimal number system. This is a code. This is not a weighted number system. This is BCD. But what's so nice about BCD is we can use this 1248. In fact, some people call it the 1248 code, and just add stuff together and write the decimal equivalent.
On this one, on the 13 I got it right. Instead of 9, I got 19.
What's that?
When did you put 9? I got 19.
How would you get 19? This is a 9. 1, 2, 4, 8. 1 plus 8 is 9. 1 plus 2 is 3, that's 1, and then 1 plus 4, 1, 2, 4. So some people call this the 1248 code. 1248. 1248. What they're doing, they're calling out the decimal equivalents of the powers of 2s. But it don't go 1, 2, 4, 8, 16, 32, 64. It goes 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. It is not a weighted numbering system. It is a code. So you can't go from here. We don't call that binary. That's not binary. It's BCD. Okay. So all we do, we directly represent each decimal digit with a 1248 code. So it's real easy to go from decimal to BCD, and from BCD to decimal, we just do the 1248 thing. But it is not a weighted number. This is weighted. So that's equal to 300. That's equal to 1100. It's not weighted. It's a 1248, right? You understand? So until we get it into the decimal numbering system, it's not a weight, it's a code. It's BCD. What does the C stand for? Coded. Yeah, it's a code. And this is the problem we have. Hexadecimal, we can go between binary and hex by using groups of 4s. And everybody gets these confused. Now, now I need to go to binary. So I'm going to come up here and I'm going to go 1, 2, 4, Rich. 4, 8, 16, 32, 64. This is weighted, right? 128, 256, 512, 1024, 4096. I don't went too far. So this is the best we can do. And then what am I going to do? I'm going to subtract this from that. People get that swapped around. They want to subtract that from this for some reason. Even though what we're trying to go from here to here, right? You understand? So we're going to subtract the highest power of 2 I can possibly subtract. I'll put a 1 down there, and I'll write down this. Subtract it. What do we come up and get?
1, 7, 8.
No, how did you? I don't know what I'm doing. Yeah, I think so. That can't be right. Yeah, I got it. Yeah, I got it. Yeah, I understand. It's usually when we call out numbers, we go from left to right. 671. And then what I do, I can't subtract the 512, so I'd put a 0 there. Yeah, 256. Okay, and what do we have? Are we okay? Okay, then I can't do a 128, so I put a 0. By the way, we're going from an odd number, so we should expect this guy right here to be set. If it comes up to be cleared, we know we want. If I don't get to 0 before I get there, I know I've done something wrong. Not before I get there, by the time I get there. Okay, can I do a 64? Okay, 64. And what does that give us?
51.
Can I do a 32? Yes. What does that give us? Okay, so that'd be a 16 and a 3. There it is. Now this is base 2. Okay, y'all understand? This is weighted. It goes 1, 2, 4, 8. It don't go 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. It goes 1, 2, 4, 8. Right? 16, 32, 64. And this is the biggest split problem we have. People seeing that as binary, and it's not. It's BCD. It's a code. Now, if I want to go to octal, what would I do? I will come up here and take this binary number and split it up in groups of 3s. 1, 2, 3, 1, 2, 3, 1, 2, 3. This is binary. And when we go to octal, we split it up in groups of 3, starting at the least significant bit, right? Okay. This would be a 3. This would be a what? 6, 5, 2. And this would be base 8. Okay, y'all understand? Yes or no? Okay. Then what we would do is we would come up here and split it into groups of 4s. One, two, three, four. 1, 2, 3, 4. 1, 2, 3. And I pretend there's another 0 out here, right? And then this would be a 3. This would be a 7. And this would be 5. This would be base 16. So now what we've got is we got the same number in 4 different bases. And they are equal to each other. It's just in a different base. You're going to run into this a lot in computers. You're going to run into both these in PLCs. This is the main number systems they use. And then, of course, decimal, you're going to run all over the place. So when you get into PLCs, you know, you can tell a lot using the decimal. There's a lot of things you can do with decimal, but when you get into your logic operations and stuff like that, you got to do binary. Decimal is just too hard. And it's just like I was talking about in networking. You know, if you don't understand networking, then these IP addresses we give them in decimal, but they are binary. Okay, y'all understand that? So in their 8 bits, they're bytes. They're running bytes. So if I got like 192.168.4.100, and then I'm trying to figure out what we call a subnet mask. A subnet mask is in decimal too, but what that subnet mask does is it identifies the network ID, it identifies the route ID, it identifies the computer ID. So when you come up with a subnet mask, if you don't understand binary, but you got to enter it in decimal, right? You understand. So what's the first thing you got to do is you'll have to take your IP address and convert it to binary. And then you'd have to take then you would figure out your subnet mask, and then you would have to convert that back to decimal before you entered it in, right? You understand? So this one good example. But we would treat these as this is called a octet, by the way, and they're bytes. Each one of these represents a byte. That's why I said you'll never see an IP address with any number in here greater than 255, and you'll never see that anyway because 255 is reserved. So subnet mask, you'll see 255. Y'all probably see 255, which is FF in hex, which is 11111. Yeah. So you start at the front, and this is your network. This is your network, and then this way is your route ID, and then on the back over here, that's your computer ID. So your network ID starts at the most significant bit, moves this way. Your router ID starts at the least significant bit. I mean, not the middle. The least significant bit move that way, but you got to leave room over here for your computer. So y'all learned a little about networking. You're gonna have, if you're gonna deal with digital equipment, you're gonna have to learn these, especially PLCs. If you get into programming of PLCs. So we okay? Any more? What's that? This guy right here. This 39. Okay. This is in decimal. I should have left my 124.8.16 code up there. So. Oops. Got to hit copy, guys. So this is base 10. This is a weighted number system. Of course, all we do with the subscript, this identifies the base, right? Make sure this number is legal in at least 2 number systems that we're going to look at. So the first thing I'm doing is we're going to go to binary. So I'm going to start writing down the chart. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 8100, 4096. So you're calling those out and you missed them. 4096. And then I always like to go one pass to make sure I have enough weights up here. Okay, you understand that? And so I know it's going to be less than 4096. And I know it's going to be odd, so I know this bit right here is going to be set, right? Okay. So what we do is we're going to, I'm going to write this over because this is a lot smaller. We're taking 3,591, all right, and we're going to subtract what from it?
2048.
2048. 2048. Okay, so what we got, guys? Okay. We can get 1024, right? I'm going to put a 1 there. 1024. What's that? 519. I can get a 512. Okay, so I'm going to put a 1 there, put a 512. Okay, that gives us 7, so we'll put 0, 0, 0, 0, 0, 0, 1, 1, 1. So once you get into here, you know, it's pretty, that last one you know. So I got down to 7. I knew it was less than 15, so it's got to go in that slot right there. And this right here is just a binary 7, right? Barry, did you do? Where'd you go? And this is base 2. Okay, so then I would go to octal. So what I'm going to do, I'm going to split it into groups of 3s. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. This will be a 7. By the way, in octal, the biggest digit you can have is a 7. It's just like in decimal. The biggest single number you can have, digit you can have in decimal is a 9. Now you can have big numbers. Okay, and this right here would be what? 0, 0, 7. This would be base 8. Then I'm going to come up here and erase my slashes. And then we'll come up here and do base 16. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this would be an E07 base 16. Don't understand. Then I do BCD. BCD is a code. It's not a decimal. I just come over here. By the way, BCD is a code, so you can't drop leading zeros. Y'all understand that? So I'd have to write 0, 0, 1, 1. And then normally what we do on BCD is we split them apart. 0, 1, 0, 1. 1, 0, 0, 1. 0, 0, 0, 1. BCD. So all we do is we write down the 4-bit representation of each one of these digits. 1, 2, 4, 8, 1, 2, 4, 8. 1, 2, 4, so it'd be 1, 2, 4, 8. So that's 8 and 1. What's that equal to? A 9. 1, 2, 4, 8. So that's 1 and 4. That's a what?
We need to memorize writing what 3 presents, 5 presents.
What do you mean? You're going to have the chart on the test. Of course, if you're going to become efficient with these bases, and like we said, good grace.
No, that's what I have a question. to remember 0011 like that, you can say or something about we need to have the chart.
You're going to have the chart.
Then
But do you remember? It depends on how much you want to deal, what you're going to go into. Of course, you know, if you're going to go into this and deal with computers and deal with PLCs, then it would behoove you to do what? To memorize chart. Because how many combinations you got? This, on BCD, you only got 10 combinations, 0 through 9.
Yeah.
But these are the first 10 combinations of the hex numbering system. So if you learn the BCD codes, then you got 6 more, now you got what? Hex. And these, the octal is here, it's just here we're using groups of 3s. So, you know, they just basically just expand on each other or compound on each other, sit on top of each other, whatever you want to say. So we have problems where people can go from here to here, but they can't go from here back to there. And I don't know, and it's one of those things. But believe it or not, it's a thing that I don't know. It's just a click or something like that. I know binary is kind of intimidating. Huh? Yeah, you've had it more than once.
But we didn't really do this, like, do it.
Yeah, because that was PLCs. This is digital. This is digital. 1s and 0s. This is digital right here. This is all. This is what it's about. All I got to do is figure out a way to represent 1s and 0s. What's the most popular way to represent 1s and 0s? Electrically. Using what? Huh? Yeah. What's the most popular way of representing? To represent digital, we got to use 2 things, right? One's got to represent a 1, and something's got to represent a 0. Now I've got to represent that electrically. I've only got 3 units electric. What's the 3 units? What's the 3 quantities? Excuse me. What we got? No, electricity. What's the 3 things we have in electricity that I can represent things with? One of them starts with a V: voltage, current, or ohms. Of course, we're not going to represent it with ohms, so that leaves me what? That leaves me volts and current. So we have a thing out there called a current loop, and that a current loop uses what? The current. The most popular way is with voltages. We just switch voltage level. Where one voltage level says I'm sending you what? A 1, and another voltage level says I'm sending you a 0. And of course, it varies between the technology of what a 1 and a 0 is. You know, I could come up here and put glasses of water. I could fill them up and make them empty. Well, I could say the empty glasses are a 1 and the 0 glasses are 0. I mean, and the full glasses are 0. So what is a 1 and what is a 0? We just got to be able to represent what? 2 different states. You got your worksheet, Barry? That was due tonight. So, so any more y'all want to see work? Speak now, forever hold your peace. I mean, it's going to be on test. A chart very similar to this is going to be. It's not going to be this chart. The number's going to be, and we're not going to have a 3,595 on the test. But
actually, it's good on the practice you give us that we can have this.
Yeah, that's what we're doing. If you can do if you can do this, if you can do the worksheet and you understand it, you won't have any problem with this.
Because one number we get, that one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th one. In the decimal, it's coming 51,679. That's a real big number. So I was just, when I got that, I was like, that I'm right or wrong, I don't know.
No, it's a big number. It's a big number. And what I wanted you to know is that binary, the numbers look real big. Decimal, they start looking smaller. Octal, they look smaller, right? In fact, decimal looks smaller than octal because octal digit only has only has what?
I was
A
so
combination.
worried about that number. I was like, I said, do I'm doing right or wrong? No, that's like, in a decimal, I'm getting 50,000 something.
And the hex is the most efficient one of the number system. This is why hex dominates now, because we can represent extremely large numbers with a smaller number of digits. And this is what I showed y'all when we brought up that system information for the computer and it was displaying all those addresses it was using in what base. And we did a memory dump on one of these machines, and even though it's binary information, the computer displays it in hexadecimal. ASCII code is a binary code, but most of your ASCII code charts are going to be laid out in hexadecimal. And like I said on that movie, The Martian, he did the hex code the ASCII code in hexadecimal, because that way he only could have 16 different combinations, right? And what's nice about the ASCII code, the first letter only goes up to 7. So it has seven columns and 15 rows. So when you get into the ASCII code chart, you read the column first, and that's your most significant character, and then your row is second. And a lot of charts you'll see in hexadecimal, because it's just a lot easier to deal with than binary, right? But this is what the computer uses right here, ones and zeros. But it knows it's trying to convey information to us. We're humans, and we really get into the problem with this. Even calling this number out right here gives us problems, right? We go to BCD, now we got a decimal number, and it gets easier. But the computer doesn't know decimal. The computer knows what? Binary. It can do BCD math now. Most of the newer processors, well, that's not true. I think they added BCD math. I think they added it with like the 286 processor, I think. I'd have to go back. It's been a long time. Any more, guys? So we okay? So let's go in and look and see what we got left in this chapter. Probably not, but I know surely they talk about codes. They should talk about codes, if not codes, I'm sorry, error checking situations. The first processors they came out with were 8-bit microprocessors. That's not true. The first microprocessor they put out was the 4004, and it was designed for calculators. And then they realized when they developed that processor for the calculators, they realized the capabilities of a programmable digital logic circuit, where instead of us coming up here and building all these AND gates and these OR gates and all this other kind of garbage, we could program this to simulate this, and then also have the ability to do math. So let's see if they talk about codes in the textbook. If they don't, we're going to talk about it. Not codes, error checking. And this might be on the I don't guess they do, but we'll talk about it just a little bit. We have several ways that we can check errors. The first way that they used was a technique called parity. And the first processors were 8-bit microprocessors. In fact, that was a good place to be. So the biggest amount of information, the first processors that went in computers, I need to rephrase that, was an 8-bit microprocessor. Now, when we talk about the number of bits, y'all know what we're talking about? We're talking about the actual size of the data that they process, or actually what we call the size of what we call a data bus. So the way a computer communicates, it communicates over through what we call buses. In electricity or electronics, a bus is a group of conductors where like information moves or power moves. You might have heard of a power bus. Well, what we have is the microprocessor. If you look at it, it's got hundreds of pins. Well, some of those pins belong to a bus we call the data bus. Okay. And the data bus is made up of, and this is what they used to define was the size of the data bus. So originally we went out and we said, okay, if I've got an 8-bit microprocessor, that means we have an 8-bit data bus. So we communicate with everybody in 8 groups of 8. And of course, this is where the term what came into play? Byte. So byte represents a group of 8 bits. Then, of course, they migrated. Then they came out with the 8008 microprocessor. And the problem they were having was we had these set size for these integrated circuits. And we'll talk about it later on. They came over here and they put pins on each side. And then we had the same number on this side as we did on that side. And this became known as what we call the dual inline package. Which everybody calls the DIP. You heard that term before? Now, these guys had to be standard sizes. The standard sizes. So, because they had all these sockets and everything made, they had layouts for printed circuit boards. So for a long time, the standard was the biggest we could have would be a 40-pin DIP. When they came out with the 8008, it was a 16-bit processor, but they wanted to keep it in a 40-pin DIP. So what they had to do is they had to let the data bus be shared by 16 bits. So what they would do is they would put out the lower 8 bits of the data, or put out lower 8 bits of data, then they'd send a signal to everybody and tell them to switch over to the upper byte, which is fun. So what we started talking about is we started moving from 8 bits and we started moving to what we call words. And what's a word? 16 bits. And then, of course, 16 bits, we moved into 16-bit processors. So now we're talking about, instead of talking about the data bus size, we're talking about the word size, right? Or how it processes information. And then what did they do after 16 bits? We moved up to 32 bits, which we call a what? Yeah. Now, Allen Bradley calls it a long word, by the way. If you get into Allen Bradley PLCs, they call a 16-bit a long word. And then where do we go from there? And this is where we're still sitting at. Yeah, we went up to the quad word. This is where we're sitting at now, which is a 64-bit word. But we have 128 pins on the data bus on your new microprocessor, because what they do is they do what they call a prefix. So actually they're pulling stuff off over here while they're working on what? This over here. So they transfer data 128 bits at a time, but they only process information 64 bits, which is pretty neat. Now, so we got all these pins that represent what we call the data bus, right? You understand? Then we got another set of pins, which we call the address bus. Now, the address bus is what we use to select who we want to communicate with. So everybody's got a binary address. So this would be like your phone number. And before I can talk to you, I have to know on your phone, I have to know your phone number, or I got to have you in my phone. I got a guy called my house the other day. I didn't have my cell phone, and he wanted to know my son's phone number. I don't know my son's phone number because what do we do now? That's a shame. Now my wife, she knows all these numbers. She don't use an address book, so she knows everybody's phone number. I look everybody up in my contact list and dial them, and I don't know my son's phone number. I wouldn't know if you saw it, but I couldn't give it to him because. So everything's got an address. So we put out an address, and this does what? This selects, and then we got the data bus, which happens what they're doing here. This is where we actually communicate. Pretty neat, ain't it? You got it? You do it? You don't have to, I'm not taking it up. I don't take up this. Here's the answer. I'll just put you down and tell me that. Yeah, the biggest processor they came out with was the Motorola 68. Oh, I gotta look that up. It was a 64-pin pack. It was huge. Well, that was the biggest DIP they came out with. What they realized is that if they started making them in a square and brought the pins out on the side, so the DIP you only have pins on two sides. If you make them in a square, what can you do now? You can do that. Then they said, wait a minute. What if we bring the pins out the bottom? So this is what we got now. We got PGA pin grid arrays. We got all kind of neat packages now. But most of your new processors, if you take them out, the pins come out the bottom because they got now where they got hundreds of pins. Because 128 pins belong to the data bus, 64 pins belong to the control bus. To reduce the size of the pins, they use multiple power pins and multiple common pins. So if you looked at like the i5 processor, there'll be about 15 power pins and about 15 common pins or ground pins. Then you got another bus we call the control bus. What do you think the control bus does? It controls the communication between when we send an address out. One of the things we got to do is tell the device whether I'm trying to get data from it or I'm trying to do what? Give it data. So we got timing. Everything is timed. We'll talk about synchronous and asynchronous. Everything's timed. So we got timing information. We got control information. We got memory control information. And another thing that's very, very popular on microprocessors is to give memory its own data bus. So for years and years, your your I/O devices, which are running at the speed of me, is out here, was sharing the same data bus as the memory, which we want to do what? We want that to scream. So now they run dedicated memory buses, and they're really, really, really changed. So we're talking about these processors have hundreds of pins. But some of them belong to the address bus, some of them belong to the what? Data bus, some of them belong to the control bus, some of them belong to the power bus. But now they have an address bus dedicated strictly to memory, and they have a memory data bus dedicated to memory, which is pretty neat. So when I say this information, or move this information around in breakneck speeds, we would like to have the ability to check for errors. Right? Now, originally the data was 8 bits. So in the first code that we used to send information was the ASCII code. And ASCII code is an acronym that stands for American Code, International Code for Information Interchange. Now, even though they had 8 bits of data to work with, they only used 7 bits. Why didn't they use 8 bits? Because they reserved most of the nickel bit for something called parity. So I would send the code. So I would send some ASCII code. And I needed, now this would be ASCII. This is not binary. Right? So what can I do with 1 bit? And this bit right here was the parity bit. What can I do with 1 bit? To indicate the number, if the number I'm sending is what's received. Can't do much with it, can I? So the technique they came up is one technique we call odd parity, and the other technique we call even parity. And it has nothing to do with the number being odd or the number being even. So let's put 2 numbers down here. Oops, sorry guys. Now, if I was using odd parity, this parity bit would be set. Now, this is a term we're going to use too, set and cleared. What do I mean by set and cleared? Set means a 1, cleared means a 0. So when I transmit it, if I'm running parity, this code would add a 1, this code would add an additional 0. If I was using what parity did I say? Odd parity. Now, what it is, even though this is an odd number, this is an even number, right? You understand? What parity does is it doesn't make, that has nothing to do whether the number is even or whether the number is odd. What it does is looks at the number of ones. We can look at the number of ones really, really fast. How many ones are in this right here? 1, 2, 3, 4. I mean, I can just look at that. And so the digital circuits that looks at this, they can do this on the fly. No big deal at all. I'm not trying to figure out if it's even or odd. I'm just counting the number of ones. So I notice the number of ones is in here is even. I want to make the number of ones odd, always odd. So what would I do with the parity bit? I would set it. I count the number of ones down here, 1, 2, 3. They're already odd. So what I want to do with the parity bit? I clear it. So that's all it does. In the receiving piece of equipment, all it does is looks and always sees an odd number of, it always sees an odd number of ones. My transmitter is the one that's adding the parity bit. My receiver is just checking to make sure there are always an odd number of ones. So when you run parity, you have to set up your transmitter and your receiver. I know it's about transmitter wrong. And your receiver have to be set up to transmit and receive the same parity, right? So both these guys have to be set up to receive the same or use the same parity. And you used to do it. It's still available now. If you got a serial port on your computer. We don't have a serial port on these machines. What I'm going to do is roadmate, but you can buy serial ports. In fact, or what we call COM ports. I heard of COM ports. Those are the old serial RS-232 standard, which is still used by Allen Bradley PLCs. So what you can do is you buy what we call a dongle. What's nice about USB is a really neat interface that you can buy dongles or go-betweens to get the old ports. So if you got a piece of equipment that runs off the old parallel port, they don't put parallel ports on the computer anymore because they took up so much space. But you can buy something that you plug in to get a parallel port. If you need a floppy disk, they don't put floppy disks on computers anymore, but you can buy them that you just plug into a USB port if you need them. We got one though. What I'm going to do is I'm going to remote into this computer right here, since nobody's using it. Oh, that's my computer in my office. I don't do that. This is that computer up there. So this computer has no COM ports or no serial ports on it. So what I'm going to do is I'm going to go in and look at this. So this is one thing you need to do. So I don't know if you're familiar with Allen Bradley software, their RS Logics. you have a program called RS Links where you go in and configure your serial port to communicate with the Allen Bradley PLC. And most people use Auto. I use Auto all the time because it goes out there and sends stuff back until it stops getting errors. So this is system information. We looked at this the other night. But what I'm going to do is, as soon as it lets me do something, that's my memory dump is still on that computer. We should have quit debug. So what I'm going to do is I'm going to bring up something called Device Manager. You can get at it several different ways. You can get at it from my computer. And then this is still also true, by the way, on the new operating systems too. And we're going to go to Properties. Come on. It's not being. Then we can go to Hardware and then Device Manager. And what we're going to do is go down to the ports. So Device Manager gives you everything that's controlled by your operating system. And here we have the COM ports. And then we have COM port 1. I'm going to double click on that. And then I'm going to go to port settings. So what we're doing here is this is the bit rate. So we're sending this at 9600 bits per second. This is referred to baud. 8 data bits. What type of parity we're using? None. And a stop bit. And then flow control, which would be, we're not getting that. But here's our options. We can run what? Even parity. We can run odd parity. We can say this device does not use parity. We can send a mark, which means it always sends a 1. Or it can send a space, which means it always sends a 0. So in communications, in the COM ports, the mark was the term they used for a 1, and the space was the term they used for a 0. I've never seen anybody use marks and spaces. This is hardware. This is software flow control, by the way. We might have time to get into that. And stop bit guarantees that we always get at least 1 bit on the end to get ready for the next start, which is pretty neat. So here's parity. So if I was going to hook this up and I set my computer to generate even parity, and I was sending it to a device that was receiving odd parity, we're going to have problems. And if you look at the ASCII code charts, I'll still have that, right? Look at that. You'll see there's some in NAC. You'll see NACs and ACs. So you look on the first few codes, which is the control code. There should be one called NAC for not acknowledge and ACK for acknowledge. You'll see that down there. Well, that was what we call handshake. So one way we could handshake is I would send it a code with parity, and then it would send me back an acknowledge code, and then I would send it the next character. It would send me back an acknowledge. I would send the next character. It would send me back acknowledge. I send the next character. It sends me back not acknowledge. I send it the last character that it didn't see. And this is one method we could use to basically guarantee that, not guarantee, or have a pretty good chance. Parity was like 95% efficient. And why is that? Parity seems, I mean, it's super simple, right? Y'all understand that? It's super simple. But what problems did parity have? Can y'all see? Where's my PowerPoint presentation? I must have closed it out, guys. But I can use this one. So what problem did parity have? Well, let's say I sent this. So let's use even parity. So I'm sending this. Well, what would the parity bit do? I'm sending even parity, 1, 2, 3, 4. It's going to be a 0. Right? Everybody okay? This went flying out. My receiver sees this. So if it came over here and saw this, oops, I messed up. I've left up a bit. Now that's what's sent. But this guy would say, okay, that's good. Why would it say it's good? Because it received an even number. So parity could not find a 2-bit change. If you had 2 bits that changed, parity would say it was good. And it's highly unlikely, but it could happen. If I've got 3 bits change, 1 bit change, 3, 4, 5, so if an odd number changes, it will find it. If an even number changes, parity won't work. And plus, parity only deals with 8 bits. So over time, it became more popular to send groups of bits. They call them blocks. Couldn't you imagine the internet if I was sending little? Once you got your shot at the internet, I send a little byte, and then I come off and let somebody else have the time. It seems like that sometimes. So that's the way most of the internet works. Is that we use something called carrier sense, multiple access, and collision detection. So the way the thing works is my computer looks at the network and sees if anybody's on it. So everybody in here shares the wireless, right? You understand? So what my computer does, it comes up here and looks at the network, see if anybody's on it. If nobody's off of it, on it, if nobody's on it, it grabs it. And it sends information, then it comes off and releases the network. Okay? I go on it, somebody's there, I come off, and it's got a random number generator, so it don't keep coming back on at the same time. It'll come back later and what? And look. And then it'll come off, come back later and look. Come back later and look. So if everybody's trying to send these little bytes, you'd be on there one at a time. But if I get access to the network, I send 4,096 bytes, and then I come off. And then I come off for a random number of time. I check it again. If nobody's on there, I send another 4,096 bytes, and then I do what? And then I come off. But if I was going to put 4,096 bytes using parity, that would be 4,096 bits of extra information I was sending, because I would have to send 1 parity bit per byte. So what they did is they came up with something they call a CRC code. It's a cycle redundancy code, right? And we can run 16-bit CRC, or the most popular now is 32-bit CRC. 32-bit CRC's got like a 99.99999% chance of finding errors. CRC 16 is something like 99.5 or something like that. So these are real reliable. What they do is they come in and they add all these bytes together. They divide it by an agreed upon, usually 5. It's usually an odd number. And then they attach the remainder, and they round it to 16 bits, or they round it to what? 32 bits. And that's what they send. The other side comes up and does what? It adds all 4,096 bytes together, divides it by the same number. If it comes up with the same remainder, it means what? The data's good. If it comes up with a different remainder, it means the data's bad. And then do what? Resend it. So this is the most popular way now. It's called CRC, cycle redundancy code. The CRC codes work with blocks of data, which is really highly reliable. By the way, they figured out that they mathematically could play around with these codes out here, and if they got a CRC error, if the CRC didn't match, they could calculate what bit in here changed, or what bits in there changed. And this came up with a method called ETC, which is error checking and correcting. We don't use that very much because it's hardware supported. If you got a big fancy server that's really, really extremely important to the computer, they probably use ECC memory in there. And the computer's got to support the ECC memory, by the way. But CRC is it now. So everything you send over the internet goes in packets, right? You understand that. And what do they use to see that? They use CRC codes. When you save information on your hard drive, it's what? CRC codes. When you save information on your USB thumb drive, all that data gets what? CRC codes. So we rip in, we do it in blocks. So when you transfer information with a hard drive, it's not a byte, it's a block. Normally 4096 bits. We call it a block size, or they call it, if you're into hard drives, they call it allocation units. Allocation units. We used to have what we call a FAT table before NT came out. And it was the file allocation table that basically kept an allocation of everything on your drive. It's a little different, still basically the same. So these are our popular error correcting. CRC is what we use now predominantly. Parity is still out there though, especially if you're dealing with a lot of things. But all the information flows on the network in blocks. Everything flows on your hard drive in your blocks. Mass storage devices in blocks. And what code do they use? They use CRC. Because now I can use 32 bits instead of having 4096 bits out here, which would be for what? Instead of having 4096 bits inside the block, I can check the whole block with what? Either 16 bits or 32 bits. 32-bit CRC is probably the most popular now. Any questions on that? So we're still using codes. We're still using bytes. So we still use multiple groups of 8 bits, right? So we okay on those terms. By the way, I was looking up a glossary of PLCs, and they had every one of those in there. So what do we call a single digit? A single digit, we call it a what? A bit. A group of 8, we call it what? Byte. A group of 16, we call it what? Word. And this is also true on the Allen Bradley PLCs. A group of 32 bits, we call it what? Double word. What does Allen Bradley call it? Long word. Yeah. So if you get into their documentation, it starts talking about dealing with long words. So we have the ability to deal with long words, and those are big numbers. 32 bits, 2 to the 32nd, -1, that would be the biggest number you could represent. Okay, so any questions on this? On chapter 1? Yes. It don't show up, it is up there. Sometimes it disappears. So we got a lab that we'll do at the end of the class. It's going to be a software lab, like I said, using, and I'll show y'all that. So we talked about octal, we talked about hex, we talked about ASCII. Of course, there's more codes out there. We talked a little about Unicode, which is pretty important now because that's what the internet uses, and that's probably what your very popular application. By the way, y'all know y'all can get Office 365 for free, right? Y'all know that, right? Huh? Yeah. It's a good deal. Going to college, all you got to have is a valid Lawson State email address. That's all you need. And if you go to Lawson State's website, it'll pop up on the scroll up there, and just go down and download that. It's a real good application. So I think we looked at this. So anytime you say insert, so now y'all going to see this. Yeah, so when we come up here and insert a symbol, there it is right there. There's Unicode. Right here. And it's actually a 32-bit code, but predominantly we use a 16-bit code. So when you come up here and click on that, this would actually be the Unicode for that symbol right there. And by the way, there's techniques I can't remember. If you know the codes, instead of hitting symbols, there's a lot of them. Some of the codes you can hit by using the Alt key on your keyboard. I can't do it on this one, but you enter Alt and then enter the ASCII code, the decimal equivalent of the ASCII code, and it'll pop up. Okay, guys, let's go into the next chapter. What's the title of the next chapter? No, I'll tell you what we're going to do. What are we going to do? We're going to take a break. In fact, I'll stop this. I'll